Okay, people, let's dive in here. This is for the especially the private group, but I'm going to put this public, especially for you guys over there. This is the back wall, the south wall, which has a lot of questions about people, engineers wanting to start it at the back wall. It's in ACI. Let's do some triangulation. Remember, triangulation is a form of psychology. That means instead of just saying that, look, instead of me just telling you, look, this is a full ledger, fully connected versus a column here, I'll use psychology, which is triangulate, is a form of triangulation is a form of psychology. So I'm not the messenger. I change it to, oh, it's not me who says it, but it's someone else. And then I use an authority that that any opposer would have to attack the authority, and the authority would be ACI, American Concrete Institute. They call this an infinite, what it amounts to is infinite support system, because the wall goes straight down. There's no, it's not set up like a beam or a girder or a header above your doorway. This is just a solid wall that the slab sits on. And so if you don't like, if you want to call this, if you get to pick between a column support here, here, here versus the wall, so here and here, don't look at this yet, versus the wall, which one would you pick that's more heavily concentrated or focused loading? Well, this is distributed. Okay, let's continue that. So this is the load is distributed along this entire wall, the southern wall, but all the slab that from here, it's some of it's in a what I call a cantilever support action, which is a critical shear zone, whether it likes it or not. Even though the reinforcement, it's because of the rigidity of it tied down to the wall below. Went over many videos with that with you. So there's a behavior, a more rigidity out to here. And now we get to the columns. If this had critical shear zones on it, remember the extra steel, then it would also have a more rigid zone, but it would taper off into the tributary area, the area between the two. And this one would be, how it would behave would be different. Think of the slab now. This is a concrete slab going from here to here. What's supporting if the slab from here, from this point, yes, this is an offset. We'll get to that again. That's that offset I talk about. This is not my drawing. These are the real plan drawings. The true plan drawings, supposedly. And the offset, you see 5'4" here. It's really 6 foot. I think it's 6'2" or 6'4". This is at this measurement, they're measuring from the face and instead of the center line. But another measurement, they'll go center line. So the offset, it's a little different here. You have to add a foot to this if you want to extrapolate out better or more consistently with the drawings. So this is a 6 foot and some change. So the offset, they even put a hash mark showing where the column should be. Oh, wait a minute. Huh. They did one down here also, and yet the column's here. So the plot thickens, doesn't it, or does not thicken? So this is where the column is. This is where they pretty much show rectangular array. This is where the cars were parked. They would have been, 1, 2, 3, and 4. This is the planter box. So this planter box, if you can overlay it, we're looking at the garage level, the floor down below, and so you have to, and you know that with the parking spots, they're labeled like this is number 72 and 71, or should I say for example. So we have there's a little dot here, right? So we have this load there. It's offset. So this is a major issue right here alone. But let's go back to the wall. So we've got to, if people don't understand they need to leave that wall alone, then you have an issue. This is what's more loaded. Each one of these column heads or the back wall. I would argue you could punch a damn hole through here, through this floor, over here, and you still got load distributing better than you have out in the columns. Oh, wait a minute. They did punch a hole in the floor over here. Okay. So, wait a minute. Over here is the ventilation spot right there. So, they did punch a hole through the floor there. Huh. Deck lasted all those years. You can punch a hole. You can punch a few holes in here. You still have greater securement here than out here. So, what's greater stressed? These column heads with the load of this deck, the weight of the vehicles and the shock loading of the vehicles, so versus the column heads or the wall. Now, I know Professor Lehman wants to, start back here at the wall. Now, I give it a 98% chance that it didn't start with the wall. And with my chance, how I rate that is that what I'm, willing to move away from that and say, okay, you can start it from the wall under the car loading back here. That it would have to have cycled over time, fracturing it here as opposed to this one. I just don't have it. Now we have a history now, history meaning recorded, that about a few weeks before the collapse, the engineer came out representing the same company did the was supposed to do the work or contracted or whatever the hell it was. They sent out their engineer to do their inspection on this area here, this planter box here. The planter box had a rotation away. And so if we put this arrow like this, that rotation away. All right, so if you do this, all right, and there's a fracture is what I'm doing there. This is not representing a fracture, this is representing an offset. So is the one at the top, representing an offset. Now, and this fracture is not visible. I visualize the stresses that way. So this is just a stress, is what I'm making clear that you should be considering. And how would that stress come about? Well, we have a down the center here. Down the center, we have what I call the butterfly failure, butterfly roof. As you guys know, I refer to butterfly roofs because in the 1950s, they look like that roughly. So as you see here, look up butterfly roof design. Butterfly roof. So you see it right there. And see the way it is? And this is what I coined the butterfly deck punching failure, because it looks like that. The support would have been there, higher up, of course, and this breaks free, comes down, and punctures through. The deck is punctured by the columns being stable, and the deck no longer can hold onto the column heads, and they fail. Now, there's a detail like this, right? That's the detail. Now, I found a report only a couple days back. This is the detail in real life, right? Don't hate me. Don't hate me. But NIST has decided that they're also going to test this one. This design. They're spending part of their 22 plus million to look at this design here with the rebar faced in like that. We clearly see the rebar was like this. So, people have agendas. I want to help out NIST. I, offered many times. I sent Mike Bell something just recently. Mike Bell, wrong person. Bell, the engineer there. Mike Bell's the guy that copies people's data and puts out videos and pretends like he all of a sudden had the idea. If you look at some of his videos, they're always behind someone else that already posted. All right, so Bell from NIST. So this is one of the ways they're going to test. They're actually going to put some extra steel here also when they test this one. These guys are going to do a little different behavior action. Scale model, I don't know how they're really doing that. Know why? They clearly had the true samples there, but if I am now trying to do olive branch Chi, meaning don't be aggressive. Not being aggressive, I would just say, well, just calmly, that this just is what's the point? What's the point? The structure the structure's heads were like that, times 4. Now, this is the size of the rebar counts there. But these only, if we're looking at it from top view, so here's top view of the column. And so direction matters, and then these are going down. And then this way, the direction matters. And as they were pulled down, the deck pulled down, it did, here's concrete cover. As this rotated down with the deck, the steel, it did spall some of this off. On this side to your left, this one, the direction of steel matters. Whether some of the columns are facing all east to west or west to east, or some of them facing north to south. That does matter. It was how it would get its reinforcement. At the pool deck area, where the engineer inspected that column area, they're turned east to west. So like that. And these are rotated down. All right, they are rotated down. They did have an anchorage ability. These things did, they spalled off. They spalled concrete off. They didn't just release. They fought. So, but I don't get why NIST, besides having agenda of wanting to just, hey, look, in the future, we'll know how this type of system behaves. This here. That doesn't exist. But clearly you can see that this isn't going to have an anchorage like that. The anchorage is going to be limited to where it's concrete, where it is engaged. And any engagement can be extended by another section of rebar that can come over and marry up to it. All right, marry up to it. But you got a small engagement. Those are like, 12-inch columns? So the best you're going to get is 12-inch overlap there. Wait for it. Or it's 12-inch overlap, but if you kept it going, now all of a sudden you just have it, this one behaving differently because it's engaging both sides of the column, of the deck, over here and here. Like a seesaw, you can't push down this one unless you affect this side, opposites. Again, I don't want to, that's just an agenda. They're just like, hey, while we're at it, we got this money, let's test this. That's what I think, all right? I'm not attacking you, NIST. Please don't come at me with shadow banning me anymore. Just saying, maybe since you do public responses, maybe you can do better with saying, what's the point of that? This didn't exist. Okay. So I'm just grabbing one of my images here, and you can disregard this or read it if you want. There's the witness, and I have him outside the deck. That's not been confirmed at this time whether he's looking through this door. As he stated, he saw I used his hands in a butterfly fashion. Left hand and right hand, if you remember his witness statement in a video. Here is the trash can, and the column is below. I'm sorry, that's high. The column would be below, supporting that deck underneath. Remember, I talk about the slab behavior and the upper, this covering slab, and it is secured only up to it is a dead load up to the columns here. But over here at the deck, for example, say I can't see it, but there's a column there, let's say, that it goes over the deck, all right? It straddles over the deck, but around here, it butts up to again. So you're getting all this weird behavior where you're getting some support and then tributary, and then it's just a dead load where it meets or comes up to columns that it does not straddle. They didn't go up. Let's do a profile of that. So here's the deck, right? The overlay. Here's the column. Let's do a different color. So here's the column. Let's clean this up. So here's the column. Let's do the deck overlay. So here's the deck overlay. And then below that, let's grab this one. This is the existing deck. So it has reinforcement through it. And let's go ahead and do that. The upper deck, and then let's do let's take some little bit of liberty here, short distance, not to scale. Now let's pull a column out here. This is the pull deck over here, pull deck. And this deck, the lower deck, the structural deck, continues over top of the columns, all right? So there we are. It's over top of the column. Sorry about the color. I know it's kind of light. And we have the reinforcement. Let's do that. The reinforcement coming up like this. And then let's make the upper deck the upper deck. Now, the overlay deck, let's make it larger. Now you can see the loads, let's change colors for you. Let's go blue. So the loads here are transferring, including this deck. They make it down over this column. You see the column? And that creates, so this section here creates it's got its own little support system, a little bit of a critical shear zone, right? All right, and over there, and it continues over to however it behaves to the next connection. But to your left here, to the left where it butts against this column, to the left here, the lower deck is engaged with the steel. All right, the upper deck is just a dead load on top of this deck. It's not, it's severed there. It just butts up to it. There is, I'm going to do a rebar here. There are no dowels. All right, no dowels there. So at the bottom here, you'll get no dowels at the deck over here. Over here, you'll get coverage. Around this pool deck, around this planter boxes, they weren't removed when this was installed, I'm assuming, that you're going to get, again, loads just going up there and loading those column heads significantly. So let's add a column roughly here. All right, so there's a column. As you can see, this upper deck will cover over it, including the lower deck. And that creates, and then here is a continuous, well, it's supported down to the slab, or at least. It's a nice continuous zone there. It's very, very rigid there, including around the pool edge. Very rigid there, very strong edge. Our back wall, same thing. So the back wall is there. And now we have that, I told you it's going to be a little bit of a cantilever effect, where it's going to be more rigid. And then this will become the tributary zone between, well, let's do two tributary zones. The lower deck has its own tributary zone, let's look green, right up to the column. All right, correction, right over the column even. Right over the column, wait a minute. Right over the columns. And let's see, back here there'll be another one. So it travels over top of that one too. And it anchors into the structure with 90s, into the drop slab detail, like that. Deck, drop slab detail. It anchors into here like that. Okay. But in the top deck, we'll go back to the pink, the overlay deck, it's because it's over that column, this is a more rigid area. That's why I did this little, made up my critical shear zone a little bit stronger, because it's over the column there, plus the deck below it. But between here, it's tributary. Oh, wait a minute. As it gets to the wall, it's still tributary. It puts us in shear also over there, just like you saw in the garage, except for this is a continuous supported structure. All right, it's an infinite supported structure at this point. All that reinforcement in there. Remember, there's 5/8 rebar at the top of this deck, and below the deck there's a number 4. There's a number 4 in the structural deck. So you got a 5, and they put a 4 down here. But I was holding out on this one, but I'll give it to you now. The upper deck, the slab above it, appears to have wire down here. Very, very nice wire. I don't care if it's at the bottom. It really holds. I think I've shown you guys how it can really behave still. So now we have this load coming down. Where is the neutral axis now? Where's the neutral axis? And once you get anything, you can get noodles, which I was going to show you 2 noodles, and I was going to put them together. I have them already. I was going to line them up, deflect them, and show you the difference. I'll do that still in another video. But I want you to see out here the behavior is going to be different than the behavior at the columns. So as you look at this would be the base deck, and then, of course, you have, which just doesn't exist. It's supposed to have a lot of rebar like this. It doesn't exist. I don't think it exists at all. But the upper deck, the deck that was added, it automatically will have some more rigidity on it. But the extra loading is still there, but it has some rigidity as it tapers off into the different zones. Let's just use those as my scaling, if you will. So this is tributary, right? Tributary zone, TZ. Tributary zone, and this is critical shear zone. All right, so this is critical shear zones. There's a behavior will be, the deflection there will be pretty different than, and here. Well, you're pretty different than when it comes to here. This is the planar boxes. The planar boxes are over there. I extended the planar box. Here's the planar box out to here. There's a BMA. I think NIST likes to now. I think NIST identified it as now Beam A. So talking the language for NIST, it would be Beam A. I'm telling you guys, there is a BMA that actually NIST did a report on. I think the 70s, late 70s. And they refer to it as a BMA, not a Beam A. Interesting, this structure refers to BMA, not Beam A. You do have a Beam A also. And they do that with, just so you don't get confused, BM-A. That's Beam A. The other one I see is BMA. There's a difference because the BMAs actually have post-tensioning to them. You actually put post-tensioning to BMAs. Now, I was waiting for some engineer to challenge me on this, but I'll just give it to you now. The document, the plans do talk about post-tensioning. They talk about it, and if that's the case, then I'm saying this is not Beam A up here. It's BMA, and BMAs get post-tensioning, and that would have been a rod, not cable. And that would have been referencing to where the BMAs were, as far as I'm concerned. They were at wherever you see BMA, like for example, here. This should be post-tensioning through here to hold that together. Here. Here. All right, this is beam 33. Beam 33. All right, beam type A, post-tensioning. It has post-tensioning in the plans, guys. Now, I hope NIST sees this and realize they need to do a correction, a change of path, a change of direction, and not take to offense. Don't kill a messenger. Don't say that jerk Kai. You know, we gotta not go there, because I know NIST. We know when NIST watches the content. But I'm just saying, you know, hey, I call myself a jerk for you. You know, just learn how to change your position. Going, oh, you know, you got data over there. You know, the data conflicts. If the data conflicts, then don't own it. Don't own it. Just move on. Say, oh, I see now where I made a mistake. So now we have this 1'6" elevation change. This was 2'6". Remember, they elevated the deck to up by 1 foot and changed that from 2'6" to 1'6". That changed everything. Changed everything. Over here is the elevation at the street. The street is 10.85 feet elevation. This is 11 foot 6 inches. And hey, Chris.
Hey, Kai, if I told you I had a plug in Florida that need people for some insurance jobs, would you be interested?
Okay, hold on a second. Let me take a let me turn off my recorder. Hold on.
Okay.
So I keep saying 11'6". I'm merging in my brain the 1'6". Right there. It's really 11'10". So the 11'6" I stated here is wrong. It's 11'10" is the elevation of the parking garage, the parking bridge deck, and the pool deck. They merged at 11'10". 10.85. That's the street elevation at the far northwest corner of the structure. If it's the street, it's pretty much level, where you come up and you look down the garage. Where the filmer was, the lady filming here, she was elevated another 4 feet. This is another video, not for this one. Maybe I'll give a piece of it. But she was elevated at least another 4 feet, plus her height. Maybe she's 5 foot. So you can see she's 10 foot up. The camera's 10 foot off the ground. 4 plus, let's say 9. 4 and 5 foot height. I don't know how tall she is. 4 foot sidewalls over there where the pool is. 9 foot. So she's pointing down. So you can see if this was the camera, this corner here. This is the center of the camera. As you look through it, she rotates her camera. This is the far right. The far right of the camera so let's see, get this right. Yep. She's out here. And the far right of the camera does like that, you know, and here's the left side of the camera. So as she zooms in, the right part of her camera is picking up that column. It's down here somewhere. And it's in the most distorted zone of the camera, of the sensor. When you look at the sensor, this being the sensor, that little red box I made, the most non-distorted area of the sensor is the center part. And then it gets distorted as you go out this direction. The further you get away from the center, which would be out here, are your distortions, the greater distortion. It's a little less there. The more you rotate the camera down, as she would have been doing, or by default because of her elevation, distortion happens again in a different axis. Another time. Let's get back to the tributary and critical shear zones again. So now this is where the planter box is. See the planter box detail here, and here's the other one, and this is the BMA going this way and this way. And I believe they did another lower box down here, and this is where the core sample was roughly. Actually, it was out here. I think this core thing comes all the way out. So it's out here roughly, the core sample. And your decking goes up to it. That deck. Well, in this case, this deck, this might be an add-on. This lower part might be an add-on after the deck. So this might go up to there. Or then again, it could go there. You know, if they reveal it, that's nice. This one again goes here. Over here, it goes to, well, right about there. Why did I stop short? Why didn't I go all the way to the wall? Can you guys tell me? There are steps over here. Remember there's steps? They protrude out, I don't know, 6 feet out or something. So it goes up to there. It didn't go underneath the steps. Even though it says 1'6" over here, there's steps over there that go into the building, into the gym. It's a continuously long step with a planter mini palm tree. Boy, I hope you're understanding this behavior of the deck, how it looks. So we got a critical shear zones is just over top of the column edge of the overlay and the lower deck. We have our tributary areas, and this is back here even, right? Critical shear. I'm doing this little arch to help you understand this, the deflective zone. Over here would be the same, okay? This side would behave differently than this side. This is the BMA, or if you want to say BMA, I will help you out with that. But remember, the plans talk about post-tensioning. So the only post-tensioning I can reference is the 1970s, what a BMA is under, believe it or not, of all people, NIST. I might have to change that to the other science research lab, but I think it's NIST. All right, we get our deflection. It's behind this one here. Our deflection is behind this one here, and that's our rotation. This is the planter box. Okay, planter box. And this is where it was re-inspected and told, it was informed that it was roots, as I understand it. Rotation. So again, 11'10". This person up here standing is looking down. They're really going to be stubby look if you can do anything from that distance. Your field of view has changed also with your camera. This is noteworthy. When they went to 11'10", on the pool deck, remember matching up with what I call the bridge parking deck, because it was a bridge. Cars drove underneath of it even. We also changed this from went to 5'8". I believe this was only 4 foot 0 inches out. They extended to 5'8". That was not the initiating cause. The point is that structurally they were changing things without paying attention, obviously. full depth. How do you get an open crack full depth? And even they do a nice little detail of it where it's open more at the top and a little bit closed, tighter at the bottom. Deflection. This deflecting, this part is deck continuing over. The deflection, rotation down, would give you your force multiplier, your fracture going up. This would should be closed, even though it says full depth. It should be closed. We have a crack here. What does that tell you? Again, deflection. This means the deck is deflecting and you're getting this opening here. I just don't get the engineers that... I know there's a lot of SI, structural engineers out there, and this is one of them, this guy here. But, I mean, you're just talking about epoxy gel. You didn't stop the deflection. The deflection is still happening. You're just trying to hold it by using glue, epoxy. Everyone I've tested on these guys, if you put that epoxy there, all you did was move the fracture over to one side or the other side. The black being in the middle there. Okay? All you did was move it to the one side or the other. The stress will still present itself right there, and it will just move to one side or the other. This one is an interesting, wherever this may be located. If you do a long beam test, I need to know how this, how this is. Is it like that? And it looks across, but this one, it looks like a certain elevation across. I don't know where this is. All right, I've got a few reasons why that would explain itself also. Yes, you get the lower fracture and upper fracture. This thing was just not taking the stresses anymore. But I want you to understand that this rotation, this rotation, a greater rotation, in fact. This one was working its way to complete its fracture. Help me. Okay, so now we're looking at, the back wall, continuous. These columns, there's a little bit of stagger on one of these, like right here, it goes down. I don't know, 6 inches. We won't even fight over this 6 inches. We'll just run a straight line. And this column row here, let's just run a straight line. Oh, stops right there. Again, we won't fight over the offsets here. We'll just run a straight line. And as you look at this again, the wall back here is continuously connected. Up there at this location, you see that so now I'm going to show continuously connected. And what's more overloaded? Span from here to here is supported only by the center one right there, the one I just put a dot on, that center column. And then over here, let's do that one. Let's go back there and let's do one here. Let's do here. Now let's continue to span over. So I want you to see these spans are only supported by those pinpoint locations. So the deck, 1,000 pounds, that's all. Okay, 1,000 pounds, that's all we're going with. So distributing load 1,000 pounds. This back wall gets to distribute it equally, how it's connected. But as it goes out, this guy has to support it. This, let's call this section here. We're going to do better than this. Hold on. Okay, so rough numbers, we're going to call this, this is 27 feet from here to here, 27. The one above that is 23. So 23 is from, this is 23. Of course, the point out here is further. It's an additional 5 feet, 4 inches, but that's that torque action. So we see there we got 50 feet. All right, 50 feet. We're going to do this. And we're going to add the, grab that zone about 23 feet. All right, just multiply it. So we come up with 1,150. 1,150 square feet roughly. And so this distance, this little zone, this little guy here. So most of that is a cantilever. The offset's over here. It's not. I'm just rescaling it differently. It's not really there. It's right. It's right here. It's right. It's literally like right here, I think. But it's got a little bit of cantilever action. It's really like that, and its connection has to go up that way to this point right here. But that puts that one corner of a table. It's like you move the leg. So here's a table, and you got a leg here, a leg here. Well, you got a continuous leg here. And then you put a leg in the middle. This leg in the middle would be this one. And then there's one leg here. So you got you put the other leg out here. As you can see, this creates that torque down here, right there. Once you torque it over as a longer span. Remember, the reinforcement really matters in here. The reinforcement, how this is done. It's a number 4 there, number 5 overlapping. High, low, really matters in the behavior, where it connects, so we can figure out the anchor points and how it's going to deflect. Well, we don't have to do much because 3 weeks before or so, the deflection showed itself. Putting it down in this tributary zone here, the butterfly zone, right down the middle. Right down the middle. Right down the line, right down the line. Okay, so this 1,150 square feet I came up with, surface square feet, and you add the 2 layers, the base deck and also the overlay, and just throw it up at 100 square feet. That damn thing's a foot thick, right? Plus the tile weight. So it's 100 pounds per square foot. The deck was designed at 40 pounds per square foot. So you're already overloading it. I know a couple of people say, you're right there, you're right there. You're right there with the, when I change it, when I put steel and I start playing around with steel, it gets very close to almost being able to do it. It doesn't do it. So remember, you're offset really here. And so this will be a point, a leg. Leg. Let me take some liberty here. Let's have a little fun. Let's do leg. Continuous wall. You can start seeing where it just, every time I play with the design a little bit, I keep getting rotation right there. And so remember, you got columns under here underneath this deck supporting it as I described to you. And there's the column there. There's a core sample there. Take note of that little green, that little line he put there, possibly for whatever reason, COVID or whatever it might have been. Oh, la 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 la. What's with the tile work? What's with this offset shitty tile work? Someone came and decided to put this design in there. All right, it's on sand and overlay. So, you know, we can read into it if you want. You'll start seeing what I call the magical bird that did it. You'll start finding, aha, there it is. That's a smoking. No. Somebody just mapped it out like that and used the full tiles instead of staying in whatever reason. So I'd almost say nothing to see there. Let's go. Almost. In this one, this is the overlay that I'm describing. And this is proof of concept of its ability to do a cantilever without just fracturing. Part of it's right here on this structural slab here, the lower slab, and here also. Oh, and you may argue that, these columns are holding it up. Well, the columns weren't there initially. After the collapse, this was nothing on top of his head. This is not touching the top of that head, because on top of that head was a slab. That was part of the thing that got removed away. It got pulled away. So the slab has an ability to cantilever, and what's holding this little angle on here is not just the rope, but there's some ropes this back up. There's some wire. They put wire reinforcement at the bottom of the slab, and that wire reinforcement helps in the mid-span, or in this case, the concrete's so it's a good concrete. The top, the overlay, it actually can hold it together in tension also. Because I don't see any wire at the top of this, not that easy to identify. The wire, okay, here's a structural slab. Here's the slab above with the wire. So here's the wire, and then the slab. So you see at the column location, it's not really needed. It just does pretty good. Just transferring down the columns area with some of the rigidity from the slab below. The slab below with its double reinforcement. It's rebarred at the top, number 5, and number 4 at the bottom. So it gets its own, by default, by being married with the system now. Not quite composite, but yes, it will react with it. And so this becomes a new critical zone for the slab above. It gets elongated. It's longer than that, I believe. So let's do that, and let's call this do something like that. Now remember, the wire's at the bottom of this. As you put your next column over here, same thing and same effect. But between the two, the wire at the bottom acts as bottom steel. And it keeps that deck flattish. As you load the top, it keeps it flattish. Of course, the deck below also gives it it has to stop some of that deflection. It helps in stopping some of the deflection. Remember, previous video I said it's like having two 2x12s on top of each other, like scaffolding boards. Even if you don't screw them together, you walk on one of them, you'll get a lot of deflection. You put another one right on top of the same one, and now you don't even have to screw them together. You can walk there, and it'll give you some, deflection, but not enough where you're going to freak out and say, let's screw these boards together and everything else. No, just two 2x on scaffolding. No, it's not OSHA approved. And this image is equivalent to looking at the drop slab detail. This is the lobby, which is up here in this white zone, and the floor would be here, anchored in with L shapes. Huh. Right there, read that question. Was this the 90 degree or straights? I think they were 90s. They look like this. As you can see, look. I'll remove it. And then back into the steel. I think they were the 90s. And they were 90s, as you can see at the upper left. So some of it came off. They're the 90s. And when the deck went down, I believe this is also how it behaved at the main structure. This is still 1 foot 6 inches. Now I got that measurement correct, I believe. Remember, I made a mistake with the 11 foot 6. It's 11 foot 10. So 1 foot 6, I believe this is the behavior you're seeing at the building also. This should be the same behavior. Same dimensions. This would be a little less force on it based it. The columns are here and here. There's a column behind this car. There's a column, short span, and yet this is what happened. And this is where that crack was, back here behind the car on the deck. There's a crack behind there, which leaves the planter box in place because the crack was preformed over timeline. Planter box, preformed crack. Preformed meaning the deck deflected some time ago and developed that crack. Remember, you saw the repairs where you see the full length repairs, and that would full depth repairs. That would be like that one. Here's the initial 2 foot 6 right there. This is before the elevation change of the deck. And we should sign right here. You'll see 4 foot, I think 0 inches. Remember I showed you 5 foot? 58, I don't know. Whatever it was, 5 foot 8 inches. Well, there it is, 2 foot, 4 foot. And remember, this is 2 foot 6 also. So right here, So I believe that would probably drop down to 1.6 also. That is just adding the rigidity of it. We're out here where our deck, our BMAs are over here. 12'9", that's a different elevation now. Correction, I think it might be the same elevation. Just the thickness has changed. Here's 1'11", and so it would be 11 inches elevation change because the deck went up by 1 foot. Let's keep it going. So I pointed to talk about the behavior of that car, and I said I think it's the same as the structure. If we look at this planter box right here, you see it pretty much is pretty much in plane. There's a shrubbery around it, and so I believe it when it went down, it behaved the same as where that car was, and you get the flatness, if you will, of it going down, and that's why it looks so 90 degree-ish. It didn't make it into the structure. I believe it just tore free just as it did with the car, as I showed you over there. Here's the one column where the inspector came out and noticed that. I talked to you about that one on the ground before. I talked to you about, well, you can't see it in this one, a fracture that leans over like that, goes over towards, biasly so, in my opinion, to what about my opinion's bias towards that column. That support for the planter box, and I believe it's did a video, and I think I said the planter box is right about the column is there. Refining that in a future video when I see the fireman standing. I believe he would have been more sure-footed, picked a more sure-footed place, so I think I might have to move it over just a few inches. And I think that at that time there was a piece of concrete over there where I found the image that he was standing on. So it seems like one of these sausages, I call them sausage links, right there, sausage link. That he was standing on. This is noteworthy. This is K9, I believe. See the ears? 1, 2 ears sticking up. Whoop. Whoop. All right, I'll move that away. So that shows the punching shear. Well, this deck is just like that. Oh, there it is. This is the one I think I might have. I'm not sure. This might be the refined one. This looks about... Oh, yeah. Maybe this is the refined one. Maybe I said it was down here. And I think I moved it over here now. Because I saw the fireman standing. Again, I think he would pick the more short-footed place. So I reserve that it could be this location. But I think I'm leaning towards this one. Just FYI, you know, you can move it over a little bit. So you can see the gate swings open. This gate swings open. It's not deformed. So... when this went down, it had it went down some degree with the deflection, and then snatched the rest of it down, acting as just a heavy load. It didn't just say, "Oh, you know what? I'm around there. Let me just drop down to here, and then I'll pull the next down." No, as it broke free here, and I'll tell you, it broke free on towards the left where the firemen are. Remember the reinforcement that I'll show you in other videos like this. That reinforcement over here, this is anchored here. This works. It's still in the deck. It's by this column. It's by the column that 2 other columns I'll show you, and this is the side that gave free, if you will, gave free, and that will be this vehicle loading side. And you can start that towards the wall if you love to, but here's the one that I stated was. Overloaded again. There's the reinforcement. You put it back up, and I think they go this way, west to east, east to west, however you want to. This is slab, however you like to think of it. Terrible expression. Gates to hell, right here. That's the butterfly area. I explained to you about that, right? Butterfly, and so that is right here. That dot there. That's where they did a core sample. They did another core sample over here. So where that fracture is, this is where the planter box stays engaged all the way over to there at least, because I can see in other images where the door is there and the slab is present. So the fracture, I believe, looks like this. Okay, where's my KLM? Something like probably deviation like that, and probably like this. In plane, I think we shift here just a slight bit. And it looks like that. Let's run the butterfly down. Our inspector last 3 weeks before did an inspection right about there. Hey, Brucey. So I have the butterfly like that. I should have stopped it at the line there for bias reasons. And then we have this one deflecting over here. So that means we have a deflective point. Here's a column right here. So that means we have to say that something's causing the deflection here. Here is our core sample that's delaminating. Delaminating, I mean, there's the rebar. Here's our deck. I showed another video, private room, I think, or Rumble. And I show you how when you get what people like to call shear fracture, we see the bottom steel eject off the concrete from the bottom. Okay, well, in this case, it's cycled many years. I believe what you're looking at is that ejection at the wall. There's a continuous system there. It's tied to the wall. The deflection and the area zones here create this delamination. Same thing over here. The deflection is too damn great. The supports or the stresses are too much with the deflection of the deck for it to hold on. It's trying to hold on with those 90s, the drop slab detail, which is here. It's even here at 11 inches, I believe. I think it's only 11 there, and maybe another foot here to gain height. It's trying to hold the deck on. And the core sample's back here, maybe, and that's a little further up. But the deck's deflecting on its own dead load. The extra loading of the top slab also. And this is happening. You're getting a bypass. I'll show it with the noodles, like I said, little noodles. I'll show it to you. Maybe in this video, I don't know. I'm almost at the hour mark. Okay, continuous support back here. Column here. Obviously, column there, face mounted. I know I'm just being redundant. Column about here. No, that's a drain. Column. Let's see, 1, 2. There's one back here. What about here somewhere? Yeah. All right, so this is offset. This one is definitely, should be up here, maybe a little bit more. Right back here. It's about a 6 foot offset from where it should be. Remember, like this? And this is about 6 foot offset. Yeah, every time I come back to this, I come to, there's our issue, and all the data supports it. And I'll end it with this one. I tie into what I have in the background for you also. You can't see it yet. There's a 6 foot I talk about. So there's your support. This is on center. The other one with 5 foot was face of. All right. This is 6 foot offset. The changes when this one is center line. There's center line of the columns. The other one was face. That's why you get the multiple different answers or different statements. Like this one down the bottom is 8. The other one might say 6. And so now you're getting 12. The other one might say 10. This one's 6. The other one might say 8. So these are all offset, though, as you can see. Look, offset, offset. As I draw them in now, let's clean that up. All of a sudden this works, right? This works back here, but the stress, remember we got the butterfly, and the great distance is the back wall. These are overloading. Car vehicles, don't underestimate the loading of the car and the planter boxes there. And the stress, the damage it caused over, oh, I'm sorry, I think I just stopped recording. The fractures it caused over time. I better do this again. I'm not sure if I was recording again. There's the offsets. Okay, Don't estimate these offsets. All right, let's just put that one in a rectangular array. What I call it triangle array. Excuse me. This one shows 6 foot. Oh, wait a minute. This one shows 6 foot. Oh, wait. What? This shows 6 foot, 6 foot, 3 foot 6, 9 foot 6, 9 foot 6. These are huge offsets, guys. All right. This is not skewed steel that hold it from column to column. This is not steel that runs in that direction. This steel is running like this. So it it's capturing everything on a torque. Now let's use the top steel as the number 5 steel. Bottom steel is 4. But remember they add the extra layer and that changes the whole dynamics of this, and also the neutral axis or how it behaves is going to change. Also, whether it's over a column or butting up to a column, the overlay deck. Some of it is dead loads as it butts up to, say this is the parking garage, up to the columns. And some of them out here, it actually goes over top of it. It can clearly go over top of here. All right, over top of here, as we see it in the video, the deck. Over here where the planter box is, though, no dice. It goes up to, and so it's just a dead stress there. Up to, over here, just dead load stressing. This one's the planter box back here, so up to, all dead load here. So where the cars park, all dead load. Dead load. Dead load. All this is dead load. This one's dead load. At the back of the building, this is all dead load. Dead loading, meaning it just goes right up to it. It doesn't go over top of it. It doesn't get the luxury. That was brilliant. It doesn't get the luxury of, I was trying to change color, of being over top of these guys out here. That might be is the line here. Yeah, these go up too, I believe. So transitioning back to the board to get the video short again. Here's your diagonal. There's your offsets. Remember these are at 9 foot or whatever you saw. There's your rotation. This is roughly the pattern of the fractures. This is the back wall. It goes down to the back wall. I just have it in a different color. I changed over to orange to make sure I let you know that's an infinite supported system. And out here is where how it would be loading differently. I'm just trying to map it differently for your loading reasons. But this is where the spans are offset, right? The rebar reinforcement's going this way. But these guys are all skewed. All skewed. These are in line, but it's also got the dead load butting up against it, and the flexion is apparent because of the fracture here, top of the deck. The core sample showing it's not bonded. Core sample there. Ending this video, you can beat it up, talk about it. Don't worry about this. This is visual line of sight for the camera stuff I was working on. So don't forget this is the infinite system. Right there. And I already talked to you about this in another video. If you're an engineer and you want to know that one again, I'll send it to you. Take care. Love you guys. Bye.